Today we'll look at the relationship between the variables that we discussed in the previous video. The relationship between these variables, the relationships between these variables, are known as the gas laws. Gas laws, as the PowerPoint shows, are mathematical equations that relate measurable variables of gas, usually two at a time, but in some situations we will combine multiple variables into one equation. Our first relationship is going to be looking at the relationship between pressure and volume. But remember that our measurable variables are pressure, volume, and temperature are the major measurable variables that we're going to talk about in this section. We also have another variable, N, which is the amount of gas, which we will continue to look at throughout the semester using a unit known as the mole, but we will not be looking at that so much right now from a unit standpoint. Okay, our first relationship, though, is going to be between pressure and volume. And when we look at the relationship between pressure and volume, we find that if we have pressure in, let's say, atmospheres versus volume in, let's go with liters, we would have a relationship that would resemble this. This is an inverse relationship. So we can make a verbal statement that says pressure is inversely related to volume. We can also, if we were to graph, I'll use a different color for this. I believe I should use something besides black. Let me use blue. If I were to graph pressure versus 1 divided by volume, what I would find is that I have this relationship. So we can also say pressure is directly proportional to the reciprocal of volume, 1 over V. Graphically speaking, whenever we do a graphical relationship, we would normally do the graphical relationship as P and V, and you would see the hyperbolic relationship. Algebraically, we often look at it from the viewpoint of the linear relationship of pressure versus 1 over volume. We could actually write the equation for this as pressure equals a constant K times 1 over V plus a y-intercept of 0, where K is a proportionality constant. Now, we can also say that this value K, which is really just the slope of this line, K is going to be equal to, just cross multiplying V times P times V. Okay. The algebraic relationship, though, is what I had here, pressure equals K times 1 over V. The proportional relationship, though, which is probably the most important, will be looking at, let's say, at 2 points. We'll call this point 1 and this point 2. So at point 2, we have pressure, or let's do volume 2, pressure 2. And at point 1, we have volume 1, pressure 1. And because of that, and we know that pressure times volume is equal to a slope, the slope is constant. So if we said the slope at point 1 is P1 times V1, and the slope at point 2 is P2 times V2, then we can say K1 equals K2, because that's the constant slope. Therefore, P1 V1 equals P2 V2. This is an important version of this relationship, and the reason for that is that K is the slope, but it depends on experiment. P1 V1 equals P2 V2, however, is a generalized relationship. This assumes that temperature and amount of gas are constant. This also has a name. This is known as Boyle's law. All right, so equation 1 for Boyle's law is this. The linear form of Boyle's law is pressure equals K times V. Both of those are algebraic statements of Boyle's law. And verbally, Boyle's law says that pressure is inversely related to volume. Okay. The relationship between volume and temperature. If we were to produce a graph of volume and temperature, we would find that we would get a linear relationship. So the verbal statement depends upon what temperature scale we're using. We're going to use Kelvin, and of course the lowest possible Kelvin temperature is 0. So we can say that volume is directly proportional to Kelvin temperature. This is the graphical relationship, and the algebraic relationship would be V equals a constant, K, times T. Now, we also know, sort of like we did in the last one, that if we find the slope at 2 points, then we can say that the slope here, if we rearrange this equation, K is equal to V divided by T, then we can say that K1, if we call this point 1, is equal to V1 volume 1 over T1, which is here. And the slope here, K2, at point 2, is equal to the volume 2 over temperature 2. And since it's the slope of a line, the slope at K1, or K1, the slope at point 1, and K2, slope at point 2, are equal. Therefore, V1 over T1 equals V2 over T2. So we have two algebraic statements, the linear form and, more importantly, the proportional form. Proportional is more important for the same reason that it was before. The value K is not universal and it depends upon the experiment, so we have different values for K for each experiment that we do. This relationship is known as Charles' law, and it assumes that pressure and amount of gas constant. Okay. Next relationship is the relationship between pressure and temperature. We find that as we increase the temperature of a gas, we increase the pressure as long as volume and amount of gas are constant. So we can say here that pressure is directly proportional to Kelvin temperature. It doesn't matter what pressure unit you use, but Kelvin is the unit here. And for instance, we could use atmospheres or kilopascals or whatever. This is the graphical relationship, algebraic relationship, following the same path that we've been through before, is that pressure is equal to a slope of a line times Kelvin temperature. And we can likewise, just like we did with Charles' law and on the previous slide, we can say that the slope at point 1, choose a point 1, and some other point somewhere else, slopes are equal at those points, and we get the linear form and the proportional form. This law is known as Gay-Lussac's law, and it is the relationship between pressure and temperature.